キヤノングローバル戦略研究所研究主幹杉山大志です。本日は米国のですね、ブレークスルー研究所からシーバーワンさんをお迎えいたしまして、再生可能エネルギー 100% という研究についてのですね、批判的な講演をいただきます。それではシーバーワンさん、どうぞよろしくお願いいたします。今日はですね、シーバーワンさんに英語でプレゼンをしていただくんですけれども、その前にですね、私の方から簡単に日本語で要約をお話ししたいと思います。で、タイトルですけども、フォローですね、中身が空っぽな研究、その再エネ 100% が可能だという研究があるんですけど、その中身が空っぽで、それ問題があるというお話です。でですね、この再生可能エネルギーっていうのはもう技術的に成熟していて、100% 再生可能エネルギーできるんだっていう、そういう論文とか本はたくさんあってですね、で、ここに写ってるのはこのバーニー・サンダースっていう、民主党の大物ですけども、この人もですね、これをエネルギー政策にすると言ってるぐらい、そういうインパクトがあるものです。100% リニューアブルがですね、こうやって非常に安いコストでですね、普通のエネルギーよりも安くできるんだということをおっしゃる方がいるんですけど、そういう研究の中身はどうなのかというレビューをしたっていうのがこのプレゼンテーションです。で、特にアジアとアフリカに関してですね、86の論文をレビューしましたと。で、中身見ると、はっきり言って非常にクオリティが低いものが多いということです。で、どうクオリティが低いかっていう話なんですけども、あまり分析がきちんとされてないっていう論文がそもそも13ですね。数字を使って計算しないと示せないはずなんだけど、そういうことすらしてない論文もあると。だけどその大半の論文はですね、研究はその計算はしているわけです。で、62件ですね、全体の 72% のでもどうやってるかっていうと、非常に単純なモデルしか使っていませんよということで、この送電線がですね、ごく簡単にしか計算されていないとかですね。それからどんな天気でも耐えられるようになってなきゃいけないはずなんですけど、そうじゃなくて、ごく限られた期間の天気のデータしか入れてないとか、そんなようなことをやっているということです。で、それからかなりの部分ですね。アジアに関してもアフリカに関しても、全体の半分ぐらいは、この緑色で書いてありますけども、一つの研究グループですね。このクリスチャン・ブライヤーという方の研究グループによる論文で、あると。だから非常に限られた人たちのグループだと。で、例えばですね、この、洋上のソーラー発電とかが想定されてるんだけれども、じゃあそこからどうやって送電線をこの島に引くのかとか、そういったことが検討されていないといった問題があると。で、それからですね、このグループの研究だとですね、100% 再生可能エネルギーっていうのは可能であるっていうことを、で、しかもそれがすごく安いってことを言ってるんですけど、それどういうことを想定してるかっていうと、とにかくほぼ太陽光発電だけで発電すると。それがこの黄色ですね。で、それがそれが太陽光がない時にはこの赤、バッテリーで発電するってなっててですね。だけどこんなに太陽光あっても余ってしまうんでどうするかっていうと、このオレンジのところが合成燃料をその太陽電池の余ったで作ると。で、赤がそのバッテリーに充電すると。で、それからこの黒いのも、これもバッテリーに充電。こっちの方は電気自動車ですね。そんな具合になっていて、もっとこういうシステムができるとも思えないし、それからできたとしても、非常にコストが高くなるっていうふうに見るのが普通だと思うんですけど、この研究ではそうなってないと。これはですね、その合成燃料をさっき作るって言ったんですけど、太陽電池の電気と、あとその空中から CO2 を取り入れて、で、それで合成燃料を作るっていうね、それも莫大な量の CO2 の大気中からの吸収っていうのを想定していて、これも現実にありそうにないと。で、この、コストの想定っていうのはすごく全体的にこの再エネについて甘くなっててですね、しかもこっちの研究からあっちの研究にコピーペーストして使っていると。で、それは他の研究のですね、想定と比べて随分安いコストの想定を置いているといったことになっています。日本に関してもですね、このリニアブル100のグループ、この LUT ユニバーシティのこのグループがですね、リードする形で、この研究、再エネ 100% 可能だっていう研究あるんですけど、 でも中身を見てみるとですね、太陽と、あと風力発電で日本の土地の 5% を占めるとかですね。で、彼によると 5% ってこの見積もりは甘くて実は 9% ぐらい必要なんじゃないかってことなんですが、これも十分、非現実的だと思いますし、それから、洋上風力ですね。これを2050年までに858テラワットアワー作ると。で、これどのぐらいの量かってことですけど、2020年の日本の総発電量が962だから、それに匹敵するぐらい、洋上風力入れるって、これももう、ありそうにないという、そういうものになっています。で、このですね、リニューアブル 100% っていう、研究はほとんど、このかなりの部分がですね、ドイツが、お金を出して、それからリードしているということになっています。ということで、結論ですけども、このリニューアブル 100% という研究はですね、実は小さいグループ、それはどういうグループかっていうと、研究者なんだけど、ほとんど運動家のような研究者のグループがやっているものだと。で、それで、その論文っていうのはどういうものかっていうと、非常に単純で、しかもとにかく再エネに有利なようにバイアスが偏りがあるということです。で、これでは、この再エネのですね、コストをきちんと評価できないと。で、実際のところはまだ再エネっていうのは問題があるわけです。そのコストの問題もありますし、それからやっぱり間欠的ですね、であるっていう問題が大きくて、出力が安定しないっていう問題が多くて、だから再エネの量を増やすことっていうのは問題が多いんですけど、その本当の問題から目がそらされてしまうのはいけないことではないかと。これでですね、この最後ですけども、本当にクリーンなですね、CO2 が出ないエネルギーシステムを目指すのであれば、もっと現実的な技術、原子力などが必要であろうということであります。
Thank you very much once again to the Canon Institute and to Sugiyama-san for inviting me to give this talk today. And thank you all very much for being here to listen to this presentation. I am today presenting on the problem of hollow 100% renewables research, which I see as a growing problem in climate policy discussions as well as energy policy discussions around the world. But before I begin talking about this topic, first I will say a few words about the Breakthrough Institute. So the Breakthrough Institute, we are a nonprofit environmental think tank and research center. We are based primarily in Berkeley, California, and we also have a Washington, D.C. policy office. We conduct analytical research and policy development. We are, however, a rather unique environmental think tank because we have a unique environmental philosophy that informs our activities called eco-modernism. And the idea behind eco-modernism is the idea that we do not have to sacrifice economic growth in order to solve our environmental problems. We can achieve both economic growth and environmental solutions through innovative policies and also through technological innovation. At the same time, while eco-modernism may sound quite idealistic, we are ultimately a very realistic research institute. We recognize that, especially in a democracy, it's important to bring many differing views together. And so we always advocate for practical policies that a large amount of society can support. So turning to the main topic, many people believe that renewable energy challenges are already solved. They believe that we already have all the technologies we need to go to a 100% renewable energy future for the world, and that this can be achieved globally and at low cost, even a lower cost than for the current fossil fuel energy system. And this is a common attitude that you see, not just in books or in news articles, but also among businesses, among government statements, and even in the political statements of some policymakers who believe that solar and wind energy are now the cheapest forms of electricity on Earth, and that we can and should move rapidly by 2050 towards 100% renewable energy systems. And where do these ideas for that 100% renewable energy systems are possible, cheap, and globally viable come from? It comes from actually researchers that claim that renewables can power the world at low cost. So essentially many policymakers, environmental NGOs and activists, companies, etc. I think that there is a large amount of academic research that has already proven that 100% renewable energy can power all regions of the world. Just a year and a half ago, there was a large-scale review paper, for example, that generated a lot of media attention. This paper on the history and future of 100% renewable energy systems research, which claimed to have surveyed the academic literature and found hundreds of studies that showed the potential of 100% renewable energy systems globally. The quote from this study says that the vast majority of 100% renewable energy system studies concluded that such systems could power all energy in all regions of the world at low cost. So this is, of course, a very impressive statement. And when this paper came out, we were quite interested in how strong this statement really was. And so we wanted to take a closer look at this analysis. So what is the quality, actually, of these studies? We critically analyzed the studies that were cited in this larger review paper, and we specifically looked at the papers on Asia and Africa, which are, of course, the world regions that are home to most of the world's population, and so are the most relevant for a global scale claim about the viability of 100% renewable systems. This group of papers was 86 papers in total. And so we reviewed these studies and asked ourselves, what quality are these studies? And we found that essentially all of these 86 papers were of poor quality, and some were of extremely poor quality. And so this finding, we believe, significantly affects the claim that cheap 100% renewables has been found by academic researchers to be possible globally. So, no analysis, discussion only. This describes one category of studies, about 15% of these 86 papers, that actually conducted no quantitative analysis or computer modeling, or very, very little analysis of these 100% renewable energy systems. Some of these papers in this category were actually only discussion papers, which only discussed the theoretical positives and negatives of 100% renewable energy systems, but did not perform any calculations. So one example, for example, is this second paper here, Mongol Dream Beyond Fossil Fuels, Prosperity of Greenification, which was nevertheless included in this review. And so this raises the question, if papers such as these include no calculations, can they really be cited as proof that 100% renewable energy systems are superior? The next category are many simple 100% renewable models that are missing important factors. So about 72% of the papers that we read in detail used only very simple energy models. So they are simple in several ways. One way is that they modeled a transmission and distribution network for electricity, essentially the network of power lines, with very few points. So, modeling very large regions of the world with, in some cases, a single point representing, tens of millions of people. And so this, of course, favors a underestimate of renewable energy system costs, because renewable energy projects are often located in rural areas or areas further away from cities, and obviously require power lines to bring electricity to the population centers where most electricity is consumed. And so this might be a factor that results in an underestimate of electricity system costs. Another way in which these modeling studies are oversimplified is that in some cases, they only look at weather data for a few days in each year, instead of looking at weather data at the scale of minutes over the course of 365 days in the year, like more advanced energy system models do. Another way in which these models are oversimplified is that they do not consider losses in transmission when you send electricity across very, very long distances, such as from Western China all the way to Eastern China, or they do not consider limits on the capacity of electricity that is able to be transferred from point to point. Whereas in reality, we understand that from an engineering perspective, only so much electricity can be transported across a wire of a given width. High number of studies from one group. So this was something that we noticed when we reviewed the studies on Asia and Africa, where almost half of these studies were actually published by a single research group led by Professor Christian Breyer at LUT University in Finland. You can see from the graph at the right that this green portion of the Africa and Asia studies was published by the LUT University's Christian Breyer research group. And this is actually the same research group that is writing the famous review papers summarizing the 100% renewables system studies. You can see on the lower left here that the review paper that we are analyzing is actually primarily written by Christian Breyer. So this is essentially self-promotion of his own group's research to a large extent. Now, what happens if we look at his studies in greater detail? What are the problems with the Breyer group's work? So this is one example of one of his studies, which looked at the Caribbean region, which is a region of island nations to the south of the United States in the North Atlantic. And so we already see some examples of the problems that I talked about earlier. One problem is that all of these countries, some of which are multiple islands, were actually modeled as single points. So there is not even a power grid in this model. The entire country, for example, the entire country of Cuba is just modeled as one single point. And then this model also suggested that floating offshore solar projects could be a very promising solution to enable 100% renewable energy systems in the Caribbean. But of course, modeling the electricity network as a single point underestimates the costs associated with offshore floating solar, because there are, of course, transmission lines that are required to bring the electricity from the offshore solar plants to the cities on land, as well as electricity lines required between the islands to share electricity and trade across islands. And so these costs are obviously not included in this model. You see similar problems in other studies. So this is the next set of problems with the Breyer group's work, looking at an example of a study that looked at sub-Saharan Africa, which suggested that a 100% renewables energy system in sub-Saharan Africa could be achieved as early as 2030, and that this system would be cost optimal for Africa, the lowest cost solution. And you can see again here in the diagram on the left that the electricity grid network representation for Africa is very simplified, with some regions with very large populations, such as Nigeria or the Democratic Republic of the Congo or Kenya and Tanzania, being represented by only 1 or 2 points. And yet that does not stop this research group from making very, very bold statements that 100% renewable energy solutions are very, very low cost. And so this raises the question of whether or not this 100% renewable energy system is really realistic. If we look at the results of this modeling in more detail, looking at a more recent study from the Breyer group that looked at the entire continent of Africa, you see in detail what they think the energy system will look like in the year 2050. In the graph on the left, you can see that this is a heavily solar and storage dominated energy system with over 3,000 gigawatts of solar projects across Africa. But as you can see from the nighttime energy generation and consumption, this is only the true demand for electricity in Africa in this model in 2050 is much lower. But the system has actually built 6 times the extra solar capacity in order to ensure that the batteries are sufficiently charged for nighttime, and also to produce fuels like hydrogen and gasoline using the solar power, hydrogen electrolysis, and also carbon capture, combining the hydrogen and the carbon to create renewable fuels that are similar to gasoline.
Siver, can you explain the color in the graph? I imagine that the yellow one is solar power, photovoltaic, and
yes. So the upper portion of the graph is generation, and then the lower portion of the graph is consumption.
Mm-hmm.
In the upper portion of the graph, the yellow is solar photovoltaic, and the red is battery discharge.
Mm-hmm.
And then in the lower portion of the graph, we can see that the red is the battery charging during the day,
mm-hmm.
and then the orange is power to fuels, which is using the solar energy to make hydrogen and also to capture carbon
mm-hmm.
and produce, using the hydrogen and the carbon, liquid fuels like gasoline,
mm-hmm.
Jet fuels, etc.
What is the blue one in the bottom?
The blue one in the upper portion is the wind generation. You see some wind generation at night.
Yeah. What about
and in
the
lower portion, that may be the power to mobility, which I think is the electric vehicle charging.
I see. So this analysis assumes that almost 100% photovoltaic system, and when there is an excess supply of the solar photovoltaic, it will be used for steam fuel and battery charging for mobility and for fixed ones as well.
Correct. Yes, this is a solar-dominated system.
So what happens if it's a cloudy day?
Well, Africa is a large continent, so I suppose they are hoping that it will not be cloudy over the entire continent.
I see. Thank you.
So this raises the question of fuels from direct air CO2 capture. And there are some unrealistic results, in my opinion, from this analysis, where by 2035, which is just 10 years from now, Africa has 38 million metric tons per year of direct air CO2 capture capacity. This is capture of carbon dioxide directly from the atmosphere. And by 2050, this capacity has grown to 55 million metric tons per year of direct air CO2 capture capacity. For context, this is an immense amount of CO2 capture. This is many, many, many times larger than the experimental projects that are operating today. And this is equivalent to capturing the mass of 527 Yamato-class battleships in carbon dioxide from the air every year. This is an immense amount of infrastructure. And this is achieved just in 10 years, when today Africa still has 580 million people without electricity. So on the one hand, this is potentially a highly unrealistic result. And on the other hand, I think this raises the question of whether or not such large investments in CO2 capture are the most valuable investments, given the large energy access problems still present in Africa. For the next problem, I want to discuss why studies use very low renewable energy costs. In these studies, we also find that the assumptions that are used to produce the findings that these renewable energy systems are very low cost are somewhat biased. For example, we compared these three studies by the Breyer team: one study for Africa, which we've already discussed, one study for India, and one study for the United Kingdom, which is, of course, a wealthy country, England. And we find that many of the assumed renewable energy project costs are copy-pasted between these three papers. For example, the CO2 capture costs, the second row from the bottom, are identical for these three regions, suggesting that you could build carbon capture plants in Africa for the same price in 2020 that you can for carbon capture plants in the United Kingdom. And then you see, for example, that the onshore wind numbers and also the solar rooftop project numbers are, again, very, very similar between Africa, India, and the UK, even though these are three very, very different regions. So this seems to be a little unrealistic. Puerto Rico, low costs, again, copy-pasted from other papers. Here, we noticed that the paper for Puerto Rico and the Caribbean was assuming very low costs for floating solar, where the U.S. Department of Energy has estimated the cost of regular solar projects in Puerto Rico on land. These are solar projects on land in 2035. And yet the Breyer Group is assuming that floating solar, which is still a relatively new technology, would cost less in 2030 than the Department of Energy thinks that regular solar would cost in Puerto Rico in 2035. And furthermore, we again find, moving to the next slide, that the other technology costs are copy-pasted for Puerto Rico from other papers, or the Breyer Group has assumed lower costs for Puerto Rico than they have for global energy projects. So now there's a fun example of the German salt caverns throughout Africa. So because they are assuming that renewable energy systems will use such large amounts of hydrogen, there's the question of hydrogen storage. In many cases, hydrogen storage might be quite expensive, but in some cases, such as Germany, there are underground rock formations called salt caverns, these large naturally occurring underground caves where people think that you might be able to store large amounts of hydrogen, like a natural storage tank. However, in their paper for Africa, which we have already discussed, the Breyer Group assumes that these salt caverns are present everywhere in Africa. They assume relatively low hydrogen storage project costs for in their Africa study, and they cite for these hydrogen storage costs, they reference a paper that studied the potential cost of hydrogen storage in salt caverns in Germany. But of course, Africa is a very large continent, and it is not guaranteed that such salt caverns would be located everywhere in Africa. So this also strikes me as an unrealistic assumption. And so moving on, these problems continue in many other Breyer studies. For example, in 2021, the Christian Breyer Research Group collaborated with a think tank in Japan, the Renewable Energy Institute, to produce a 100% renewable energy pathway for Japan by 2050. And again, we see many similar problems. First, again, the electricity network is very simplified. Just a few points, as you can see. But there are also some rather notable results. For one, the researchers found that they set limits for what they saw as the realistic limits for solar and onshore wind deployment in Japan, given the land scarcity. And the model reached those maximum limits for solar and onshore wind. So they were unable to deploy any further solar and onshore wind. And this amounted to a total of 5.1% of Japan's land area in their study. However, I performed my own calculations based on their results, and I think that this might be a conservative estimate, and that the true land area usage might actually be closer to 9.3%, which is a rather large amount of land area. Furthermore, because they were unable to deploy any further onshore solar and wind, the model ultimately deployed a large amount of offshore wind generation in order to achieve a 100% renewable energy Japan in 2050. This totaled up to 858 terawatts of annual generation from offshore wind. And again, this highlights several problems. First being that the power lines to transport the electricity from these offshore wind projects onshore in Japan were not modeled. And second, this is a very, very large amount of offshore wind electricity generation. For comparison, the total national 2020 electricity generation in Japan was 962 terawatt hours. So this is the equivalent of generating as much electricity as all of Japan generates today from offshore wind, which has still been deployed only to a very limited extent in Japan by 2050 in just 25 years. And then the study, of course, the study is rather anti-nuclear and decides to phase out all of Japan's nuclear power by 2030. So moving on, one thing we found when we looked at these studies is that much of these works are German-led and German-funded. So, for example, the study I was just talking about for Japan, as well as studies for Indonesia or Taiwan, have been supported or led by German think tanks such as Agora Energiewende and the Energy Watch Group, and in some cases have even been directly funded by the German government, such as the Japanese study. So this is rather interesting considering that Japan's energy policy is also 100% renewable energy policy that is very anti-nuclear. So now moving on to my conclusions, it seems clear to us after having reviewed these renewable energy studies for Africa and Asia that much of this research and thinking seems to come from a very small group of researchers who are almost like activists. They are very anti-nuclear and they are very, very optimistic about the future of renewable energy. Their research papers seem to be overly simple and biased in favor of renewable energy. And I think it is fair to say that they cannot accurately model the true cost of 100% renewable energy systems. And so I think this is problematic because while renewable energy may be an interesting technology with future potential as the technology continues to evolve, in reality, global challenges for renewable energy systems remain very difficult to solve. And so I think that oversimplifying these problems and making it seem as if these problems are all already solved is quite misleading and problematic for moving forward more concretely. I think real progress towards clean energy systems will require much more realistic and problem solving and much more honest research. And I think it will also require considering other clean energy technologies like nuclear energy, perhaps carbon capture and others. And so overall, we need a much more honest research approach, and I think we need to come to terms with the fact that not all of the problems with renewable energy technologies have yet been solved. Unfortunately, I think that it is still very much the case that, broadly speaking, in the political community, among environmental NGOs, and also among many leaders of companies and so forth, people still have this misleading idea that the research has already been done and that 100% renewable energy systems are proven to be the optimal solution, when in reality, this may not be the case. So that concludes my talk, and I want to, again, thank you all very much for taking the time to listen, and I'm very much looking forward to the follow-up discussion.
はい、この後ですね、私との Q&A セッションに入りますけど、英語でやる前にですね、その簡単に日本語で要約だけお伝えしておきます。で、質問は全部でですね、5問あります。で、最初がですね、このシーバーワンさんのこの分析に対してどういうリアクションがあったかっていうことなんですけど、きちんとしたその技術的な評価をやっている人たちからは非常にその通り、私が思ってた通りだというようなリアクションがあったと。で、その一方でですね、リニューアブル100推進している人たちからは批判もあったんですけども、で、ただ批判あってもですね、いくらかやり取りして具体的にこことここが変でしょって話をすると、そこはそうかもしれないと。ただそれでもリニューアブル100っていうポジションを変えるというところまでは至らないことがあるということです。で、それから二つ目ですけど、再エネを入れすぎたことですでにもう、電気代が高くなるとか問題が起きているところはいくらかあるんじゃないかと。ドイツとかカリフォルニアとかいうことで、それはそうだっていうことなんですけど、ただその、再エネの導入だけが問題なんじゃなくて、結局、再エネ導入しても、ガス火力もなくせなくて、で、そのガス火力の値段がですね、ガスの値段が急に上がったりしてて、そういった要因も、価格上昇の背後にあるということです。このリニューアブル 100% っていう研究がですね、現実世界に悪影響を及ぼしているかっていう質問をしたんですけども、実際のところしてると、さっき言ったようにバーニー・サンダースとかですね、アメリカの大統領候補の大物みたいな人がこの再エネ 100% っていうようなものを、実際の政策にしてしまっているとか、あるいはアフリカに対してですね、この再生可能エネルギー 100% っていうものを、事実上押し付けているというような援助機関とかがですね、太陽風力などにしか支援をしないと、その他の火力とか原子力の支援をしないということに陥ってしまっていると。だからこれは実際に悪影響があるということです。 で、それからなんか一種自己矛盾なんじゃないかっていうことを私は質問したんですけど、その再生可能エネルギーがもし本当に一番安いなら、自動的に入るはずだから、政策的に入れる必要なんてないでしょうっていうことなんですが、それは実際その通りだと、ワンさんも思うと。で、プエルトリコの話とか出てきましたけども、ああいうところは火力発電も非常に高いので、本当に再エネが安いんだったら、そっちは自動的に入るはずだけど、そうはなってないと。結局まだ再エネのシステムは実は高いんだということです。で、最後にですね、今回レビューした論文っていうのは、一応ピアレビューですね、お互いに査読をして、で、学術誌に載ってるんですけど、それは機能しているのかと、初歩的な検討でもアウトになるような論文がなんでこんなに通るかっていう話なんですけども、査読システムってあるんですけど、結局仲間内でやってるだけで、その仲間内でやってるジャーナルでそういうものが通ってしまっていると。そういったことのようです。それでは、これから英語での Q&A 詳しくお聞きください。Okay, thank you very much, Siver, for the very clear presentation. Let me ask you a couple of questions now. The first one is what has been the reactions from the audience who listened to your presentation, your publication, and particularly from all those people who are promoting renewables?
Yes, I received a wide variety of reactions. Mm-hmm. So some reactions were quite supportive. Some people, even if they, especially more rigorous energy researchers mm-hmm. had already thought the same thing about these studies, that they were low quality, and so they were very grateful that other people were noticing the same problems, and that I had sort of done this detailed review. Now, among people who are very devoted supporters of the 100% renewables energy thinking, I did end up in a number of arguments. Some people thought that I had made some thoughtful criticisms, and so they thought, okay, I will maybe think a little. Other people really strongly disagreed, and so we had some long arguments. And maybe at first they were very offended that I was criticizing these researchers that they very strongly admired. But then as we discussed in detail, they came to realize that I had, really read these papers in detail. And, I talked to them about very specific points like this assumption, this cost, this model structure. And they actually, in some cases came to agree with me that I was identifying real problems. Even if they still are, didn't change their mind on 100% renewable energy thinking, they still came to agree somewhat that I was noticing problems that were real.
Mm-hmm. It seems to me that there's already too much renewable penetration in some regions on the globe. I can think of Germany. There's been a lot of windmills and the photovoltaics installed, and now they are facing very high electric prices. And it looks like the California, where you're located, more or less the same with Germany. Am I correct?
Yes, that is the case. In many cases, it's related to multiple factors. And many of them are related, are made more difficult as you keep adding renewables to the grid. So in both the case of Germany and California, some of the problems are, one is that a large amount of grid upgrades have been required in order to accommodate these solar and wind farms, which are being built in new locations. And so that requires new power lines or upgrades of existing power lines and so forth. In some cases, the electricity consumers, like the households and companies, are having to pay for some of the subsidies that have been given to wind and solar projects. For example, in California, customers such as myself are paying for some of the other rooftop solar projects that are on the grid. And then I think the biggest issue is that currently there is no good renewable energy replacement for gas power plants. Wind and solar cannot currently replace the on-demand sort of reliability of gas power plants. And so this has resulted in electricity markets where the price of electricity is set by gas. And fossil fuel markets are sometimes very volatile, especially because of global events like like Russia's war in Ukraine and so on and so forth. This has sometimes resulted in gas shortages, which has meant that the price of gas has gone up very, very high. And because gas is still the foundation of energy systems, even in regions where there is more wind and solar, this means that the system ends up being much more expensive. So I think these are some of the problems that are affecting these systems. Although, it's always complex. There are other factors as well. For example, in California, there are many grid costs because of wildfires that have happened in California. And so the utility is having to upgrade wires to power lines to reduce the potential risk of starting fires.
Let's see. In your presentation, you said that Renewable 100 research is causing the problems. Is it causing the problems in the real-world energy policy?
Yes, I think so. We still see, for example, one of the pictures I showed in my presentation showed one of the U.S. Presidential candidates from 2020 who actually cited some of this research as part of his energy plan, which would have wanted the U.S. to transition to 100% renewable energy by 2030 while shutting down all the nuclear plants. So this was a serious presidential candidate who was second place in the Democratic Party nomination in the U.S. in 2020, who really believed, his team really believed this research. And I think we see results in many countries like Germany and Taiwan, and also many U.S. states, for example, that have committed to transition not to 100% clean energy, but to 100% renewable energy specifically, who are inspired by this research. And I think this also affects developing countries because institutions like the World Bank or, for example, the German development banks believe that 100% renewables systems are not the cheapest option, and so they refuse to consider any other solutions, whether that's hydroelectric power dams or nuclear power projects or carbon capture or gas projects in Africa, for example. They will no longer fund these projects. So I think it's causing a lot of real-world policy problems.
I found it sort of contradictory because on one hand, they claim that renewable is the cheapest, but on the other hand, they want policy to implement it. If it is really indeed cheap, then there is no need for policy, aren't they?
Yeah, this is a contradiction. And I think actually looking at the developing world or at island nations highlights this particularly because energy is already very expensive in places like Nigeria or Rwanda, or in island nations like Cuba or Puerto Rico, or the island territory of Puerto Rico or Jamaica. And so because the existing fossil fuel energy system is already so high cost, if solar and wind and batteries alone were already cheaper, then these countries would be buying large amounts of these technologies. And so the fact that they are not doing this suggests that clearly the picture is much more expensive. And I think to a large portion, the answer to this is infrastructure and also the reliable baseload energy. Because upgrading the power lines is very expensive. And then ultimately, you still need a electricity source that you can switch on and off when you need it. That's not weather dependent, and that's not very limited in capacity like batteries are.
Okay, the final question is that I think that all papers you reviewed, 80 several, so-called peer-reviewed academic papers, but in your assessment, it lacks I would say, a very basic analysis of from the Bureau of Electrical Engineering. But still, their so-called peer-reviewed papers, it looks like almost the meltdown of the academic systems of publication.
Yes. So I think in some cases, you get the development of sort of tribes or parties or factions within the academy that are all peer reviewing each other's papers.
Right.
So because these papers are part of the 100% renewable energy system studies community, the editors of these journals are sending these papers to other people in the 100% renewable energy systems community for peer review. And so it is a question of friends reviewing their friends' papers. And so they're not subjected to as rigorous peer review. I think, this is not, I think fortunately there's still, many other areas of academic science, like the medical sciences or chemistry or physics, where this is, not the case, where papers are much more rigorously reviewed. But in some cases, you get the development of these small cultures where the peer review process is being somewhat bypassed. And I also noticed when we were reviewing these studies, in many cases, they are not papers in the most prestigious journals. They are often studies that are being published in middle tier or even lower tier journals. And so the standard for publication may also be lower, and maybe the editors are less aware of how rigorously they should be reviewing the studies.
Okay, thank you very much for the very clear answers to my questions. And thanks again for the clear presentation. We have learned a lot from your analysis.
Thank you very much for the thoughtful questions, and thanks once again for the invitation to discuss.
Okay, thank you very much. Goodbye for now.
Thank you.